Okay, we're going to go ahead and get started. So this is our 2:30 press conference, Postcards from the Edge of Space. New images, new phenomena, and new insights. And our panelists today are Jennifer Briggs from Pepperdine University, Richard Eastis from the University of Colorado Boulder, and Thomas Immel from the University of California, Berkeley.
Awesome. Let's see, does that work? Okay. Hi, everybody. My name is Jennifer Briggs. I'm actually a senior undergrad student at Pepperdine University in Malibu, California. And this summer, I was given an awesome opportunity to attend an internship at NASA Goddard, where with the help of my amazing mentors, Gerard Fazal, David Sybeck, and Marco Silveira, I was able to make a very exciting discovery concerning the ionosphere of the Earth and the solar-terrestrial interaction in general. So this talk is about the Earth's ionosphere. What is the ionosphere? Well, the ionosphere is this amazing mixing pot of all of these particles. Some have bubbled up from the Earth and are now interacting with particles that have come all the way down from the sun. And these interactions can be incredibly turbulent and confusing, but they can have very important impacts into life as we know it. These interactions can cause things like technology issues, blackouts, and even impacts on human health. So it's very important what we're studying. But all of these interactions are completely invisible to the naked eye. That is, until now. So this talk is about how each of us have figured out ways to make the invisible visible using different scientific techniques and spacecraft data. So I'm going to start with talking about how the ionosphere is impacted by the sun and the incredible impact that the sun has on Earth itself. And then my colleagues are going to talk about the ionosphere and the Earth. All right, so let's start with the sun. Oh, that's my name. Okay, so the sun is this very active place that's constantly streaming out what is known as solar wind. Solar wind is filled with charged particles that rush through the entire solar system at hundreds of kilometers per second. And it's very dangerous. But we have ourselves a bit of a magnetic shield called the Earth's magnetosphere. And it protects us from the harmful effects of this solar wind. But when the solar wind is strong enough, such as in coronal mass ejections, it can compress or even erode the Earth's magnetic field and cause things like I was talking about, these blackouts, technology issues. It can hurt the internet and cell phones and even cause human health issues. So these compressions are very important. And exactly 3 years ago today, a massive compression hit the Earth. This was seen on MMS, which is a spacecraft that was sent to explore the Earth's magnetic field. And in 1 minute and 45 seconds, the entire magnetosphere, which is where the solar wind and the Earth interact, and the bow shock, which is caused by a supersonic speed of the solar wind, all rush past the MMS spacecraft fleet. Now, to give you an idea of how incredible this distance is about 4 Earth radii. And that means that if I were to send a jetliner, a commercial jetliner, through this distance, it would take approximately 27 hours. So 1 minute and 45 seconds is an incredibly rapid and dramatic compression. But confusingly, there was nothing significant going on the sun this day. No coronal mass ejections like I talked about, and no solar flares. So not only have we never seen a compression of this intensity, we've never even predicted one. Further, we don't currently have the technology or the spacecrafts available to understand or see the energy transfer going on outside of MMS. And so that is where the ionosphere comes in. The ionosphere acts as a bit of a movie screen to allow us to then visualize the invisible things that are happening out at the magnetosphere. Why? Well, as you can see, the Earth's magnetic field is made up of what's called magnetic field lines. And these act a bit like strings. And when the solar wind smashes into these strings, it causes ripples to go through the magnetic field lines. And just like a surfer catching a great wave, an electron can catch one of these waves and ride it down into the ionosphere. And it can interact with neutral oxygen and nitrogen atoms, letting out these green and red lights. And that is what all of us know of as the aurora borealis and the aurora australis, or the northern and southern lights. So we can use these lights to see what's going on at the Earth's magnetic field. down into the ionosphere. So when we track this compression all the way down into the ionosphere, I found that it was located just over an island over Norway, where our friend Fred Sigurnes is the chief scientist of Kjell Hendriksen Observatory, and he was able to provide us with this data. Now, this is a video of the aurora at the time of the compression, and this motion is something that we've never seen before. This eastward and then westward and this spiraling motion is not something we've ever seen, not something we currently understand, and we also don't understand the drivers, so it's incredibly significant. Further, this is the first time we have ever seen an ionospheric signature of a massive compression, and you guys are the first people to ever see it. So it's very, very exciting. But even though we don't fully understand this, what we can know is what it tells us about the compression. Since the compression only innervated a spot just over this part of the ionosphere over Norway, we know that the compression is localized. So while massive, the compression is actually quite small. So, using all of this information, we can also tell that a small compression like this most likely didn't come from a driver in the solar wind, but came from a turbulent area just outside the magnetosphere called the foreshock. And with all this information, we can then visualize the invisible compression in my attempt at some graphic art in this incredibly intense, rapid, but localized compression. And for this reason, we're naming the compression a foreshock-generated localized compression, or an FGLC. And the aurora is being called a foreshock aurora because it was created by a transient in the foreshock. So this is important for multiple reasons. One, this is the first time we've ever documented an ionospheric signature of a massive compression. Two, this proves we had no idea that a transient in the foreshock could have such incredibly massive implications into the ionosphere and the magnetosphere. So it's incredibly important for our science. And three, this reminds us just how important it is to use multiple spacecrafts and multiple data sets to understand what's going on in the solar-terrestrial interaction. And with that, and especially data sets that can show us how to visualize the ionosphere and make the invisible visible. So with that, I get to turn it over to my colleague Richard Eastis, who is going to talk about a spacecraft that does just that.
Thanks, Jennifer. Hard act to follow. Okay, but I'll try. Okay, so let me. So anyway, I'm the PI for the Gold mission. I'm Richard Eastis, PI for the Gold mission, and of course this is one of the images that we've taken for the Gold mission. You know, I won't try to tell you this is the typical image. It's slightly atypical, but I'll explain why in a moment. But we do see images like this every day. We image at a regular cadence, a half-hour cadence throughout the day, at least throughout the day. You know, throughout the except for 6 hours around midnight, or 5.5, 6 hours around midnight. So, you know, of course, Jennifer was talking about the aurora. That's what you see up here at the top of the image. Of course, this is a relatively quiet time when this occurred, when this image was taken. When it becomes active, geomagnetically active, we typically will see the aurora come down here further south, and of course, this produces a lot of ionization in the atmosphere, a lot of energy. Those particles coming in along the field lines are basically have a lot of energy. They create a lot of ions around 110 kilometers or so, about 60 miles up in the atmosphere. Now, one reason this is important is because you know, a lot of the routes when you're doing international travel are flying near the poles. So when you're flying over there, you know, the airlines, they like to have their planes check in occasionally. You know, like how when you're a kid, your mother wanted to, or your parents wanted to check in occasionally with them to sort of let you know where they were or where you were. The same thing with the airlines. They'd like to know occasionally hear from them. So when things get really active, it actually interferes with the communication. So they actually have to reroute some of the planes to further south to avoid the area where there's a lot of activity, so they can communicate with the planes. They will actually do that. So there's also some radiation risk, but anyway, it's mainly communications, as I understand it, is reason for the change. So anyway, that's at the high latitudes. The other, of course, that's auroral particles. The other source of energy from the sun, of course, is the X-rays, the soft EUV, really energetic photons, and that's the source of all this, what you're seeing over here. This is, sometimes we call this the day glow or the daytime air glow. This is emission that's created by the photons from the sun getting absorbed in the atmosphere, creating energetic electrons that basically excite the gas up there in the atmosphere, causes it to glow. And we're looking, of course, at UV wavelengths. So these wavelengths you can't see from the ground, and we can't. Unfortunately, we actually can't see the ground, and so we can only see the upper atmosphere. So that allows us to look at this part of the atmosphere by looking down from geostationary orbit, where the gold satellite's located. So, and actually, it creates not only when the absorption occurs of the photons, it also by pulling electrons, or ionizing the gas there, it actually creates the ionosphere in the daytime also. And then, of course, at night, here on the right-hand side of this image, you see the nighttime ionosphere. So this is a sort of a fossil or sort of residual from what was happening in all the ionization that was occurring in the daytime, that in the equatorial region, near the north and south of the magnetic equator, which actually sort of tilts down over South America here, you actually have, because of the way the winds flow and pushing the ions across the field lines, you have the ions getting pushed up to high altitude where they don't recombine. They're recombining in the daytime, but we get extra ions in these regions on each side of the equator typically. And I'll give you a little bit of a foretaste here. You see all this stuff in the middle here, and some of that actually is something that gold is able to image, and we actually sometimes call these depletions, where there's a lack of ionization. That's what causes a lot of the trouble, our biggest part of the trouble at night. Anyway, let me go on. So there's two times that this sort of nice, smooth stuff in the daytime gets interrupted. There's some of the times it gets interrupted is one of them is when we have a geomagnetic storm. And I play here a movie that was an example of what gold observes. This starts on the day before the geomagnetic storm. And when the storm occurs, which is the next day, you will see it here, and you will see that the composition, which we're looking at the atomic oxygen to molecular nitrogen, so it's the ratio of ratio of these species in the upper atmosphere, how when we have a storm, that can cause this ratio to change, and it actually, with all the heating in the rural region, it pushes the molecular nitrogen up and into the higher altitudes near 160 kilometers where we're looking, where gold is observing. So it's observing essentially a layer at about 160 at actually constant pressure height, we sometimes say. So this is well, I don't know. It's like what? It's the same day. It keeps looping on the same day here. So somehow it didn't. I don't know what's happened here. It's the movie. Technical difficulties, but it keeps looping on the first day. It doesn't go to the second for some reason. I don't know what happened. All right. Sorry about that. I think on the website we will have the one that does actually go to the second day. At least it doesn't come out on the screen here. It's not coming out. So the other time that we actually had an opportune time to see how things change in the daytime, the air glow, because we can use these emissions to look at the composition and temperature of the upper atmosphere. So, and by the brightness and how things change. So we also had some observations during a solar eclipse that went across South America. So this solar eclipse, of course, we start the observations here. This is I know I've run it a time or two, and this certainly will work better, or should anyway. So here we go. So what's happening is it shows how the imager, gold imager on the right, it scans northern latitudes and southern latitudes. It's going back and forth. This is the reason that terminator, the edge between dark and the night and day over here is sort of shifting at a different rate in the two latitudes. So it's sort of course, they have the visible when the eclipse comes across about now. No, it's the next day. I'm sorry. It'll start with show that the path of the eclipse over down here at the bottom. Path of totality, I should say. Actually, the eclipse itself covered almost all of South America, at least partially. The partial eclipse occurred throughout South America, except for the very northern latitudes. So you can see that it changed the mission quite a bit. There's certainly some things we don't understand about this, because when we do some of the modeling, we're seeing quite a bit more temperature change, for example, than we expected in this, so we don't understand that. So, okay, I've talked about the daytime air glow, how that changes. Let me go to the moment to the nighttime air glow, or the equatorial ionization anomaly. So as I mentioned, this is what's called the equatorial ionization anomaly. So the pictures we've always had of this at least that I've always had of this, is it's relatively smooth, and that there's sort of these two regions of enhanced ionization on each side of the equator, about 15 degrees from the equator typically, that this is occurring. And and occasionally, as mentioned, we have these regions in here called depletions, and that's, of course, those are really bad news. It looks like there's nothing there in the ionosphere, but actually there's some very important stuff going on there, because at the edges, and I think you can see some of them in here. I don't think it's showing up quite as well on the screen as it shows up on the images that you can download online. But there are some and you can see them in that earlier image, how there's depletions there, but they will go all the way through the equatorial ionization anomaly. It looks like there's nothing there, but radio frequency propagating through the ionosphere, actually there's a lot of turbulence, a lot of small-scale variations at the edges of them. That scatters the radio frequency signals. So it causes problems for the propagation for GPS, for communication signals, and such. Now, as mentioned, we typically think of this as occurring about 15 degrees from the equator. What we've seen on gold, which is sort of a surprise to us, back to Jennifer's talking about how some of these things, they were seeing things occur when there wasn't really a lot of traditional geomagnetic activity. We see things occasionally here that shift by 15 degrees further away in latitude. So 15 degrees, if you think about it, in latitude, that's equivalent to about the distance between, distance from Washington, D.C. to Miami, or if you're on the West Coast, it would be Seattle to Los Angeles approximately. So that's about about 1,000 miles is what it's moving the position. And of course, again, this is okay, why do you really care? Well, high latitudes, you don't have as many people, human activities you do at low latitudes, and you have some of the same issues with communications through this. When you have flights flying through here, so you can actually see some bubbles in here, and depending on where this ionization is occurring, it changes your communications properties. It can interfere with your communications because of these bubbles. So, of course, we see them go far apart when there's really nothing traditionally geomagnetic, no traditional geomagnetic activity we're seeing. We just see them just move 15 degrees, which is a lot apart. And also at times we see them go collapse, such that they move 15 degrees inward. And the same thing, it's sort of like, okay, this is moving all over the place. This is not what it's supposed to do. So, okay, so we don't know what, we don't really understand this well enough. We don't, we have some guesses at what's happening, but as to what's really happening, okay, it's still a question. And anyway, the equatorial region, the ionization there is an interest of, certainly a topic of great interest, enough interest that Tom Immel, as the PI for ICON, has a mission that just was launched recently that goes and looks at this region. So I'll turn it over to Tom.
Thank you, Richard. Hi, I'm Thomas Immel. I'm at UC Berkeley. I'm a researcher, and I'm the principal investigator for the ICON mission. When we set out with our mission design and proposed it to NASA, and NASA selected our mission at the same time as GOLD, I was sure we would launch before Richard, and I was how wrong we were. But Richard's mission has been up there for a year. We just launched on October 10th, and we just went into science mode November 1st. So we've checked out our instruments. What I'm going to talk to you today, what I'm going to show you today are some of our first outputs from our instruments and talk about how those instruments are going to help us address issues like this one. Richard's GOLD mission has shown us just a ton of great examples of how variable the ionosphere is from one day to the next. And funny that that's our top priority for the GOLD mission, is to understand and investigate this region of space and understand where that variability is coming from. So the GOLD mission has really wet our whistle, as it were. So this visualization shows how GOLD and ICON can work together. ICON was launched out of Florida and into a 27-degree inclination orbit. That means that the highest latitude it ever reaches is plus or minus 27 degrees. So we're flying near the equator. And GOLD's scanning every half hour over basically over our field of view. Or I should say that every 90 minutes we fly through GOLD's field of view. So what GOLD sees, we're seeing, but in quite a different view. From our vantage point, we point our instruments, instead of straight down to the Earth, we point off to the horizon, where we can see all those emissions that Jennifer and Richard have talked about, but in an edge-on view. So we can do altitude profiles and retrieve a number of key parameters of the system to try to understand the variability. So this gives you a quick picture of how that can go. So the fields of view shown there are the big central cone, or we have UV instruments working in the ultraviolet, just like GOLD, but again with a different vantage point. At least we're working in the ultraviolet. We make the measurements in a different way. I'm going to talk about it. We have two cameras, actually, an extreme ultraviolet and a far ultraviolet, and I'll show you some samples. And then the two sideways looking cones are two wind interferometers. They're interferometric observations in the visible at the same red and green emissions that you see in the aurora. They're actually being emitted at low latitudes as well. And I'll show you some examples of that instrument working and some examples of the science target. So what I first want to show you is our first image from our EUV instrument. Before we can look at the Earth in the extreme ultraviolet, we need to understand, the first thing we did was actually point it to space and try to get some calibration data. And I learned a lot about our local universe by looking at these calibration data that Martin prepared. This movie. So what am I showing you? We have a spectrometer that separates the light into its different frequencies in this direction and has spatial resolution in this direction. So those little stripes you're seeing, what are we pointing at? We're pointing at the moon. And we point at the moon at 7 different steps in the imager. We take the imager, which has a field of view, if you hold your hands out about like this, and you can look around. We put the moon in there. And the moon that's what the moon looks like in our imager. It looks like a stripe. Why does it look like a stripe? Well, it has different emissions in the extreme ultraviolet. So those emissions are spread out. And we're stepping it, and you see how we're collecting data, collecting photons. We count one photon at a time, and we collect all the photons that the moon's putting out in several different colors in the extreme ultraviolet. The other feature in this image is this giant stripe, and that's our local universe, or I should say our interplanetary environment. That's a signature of helium, ionized helium. Where's all that coming from? It's coming from the sun. The sun and the solar wind, which you heard about, is full of ionized helium, and the whole our whole local environment, our space environment, glows in that color. And the sun is the rest of the solar spectrum, which has a number of different lines that aren't coming back from the solar wind at us, are bouncing off the moon. So it's a great calibration source because we also have an SDO, another NASA mission that's looking at the moon and measuring that extreme ultraviolet emission, and we have a great calibration source for this instrument. If the next slide shows you, well, ta-da, if you point and look at the Earth, you see something quite different. Wow, look at all this stuff. So there's the helium line. There's the oxygen line. That's the ionosphere now, which was not there. You know, no oxygen, but now we're back. And these are a number of different, very faint oxygen lines that we have a lot of capability to see now. We're excited about this instrument. The next instrument is a spectrometer, but it works a little differently. We decide which lines we're going to work with, and we take images at those lines. So we would take an image at this line and an image at that line, for instance, and that's what actually we do. I'll show you let me just get to it. This movie shows the view from our FUV instrument, looking at the Earth in the far ultraviolet. This gives us a view of the day and night. Again, but the feature of the ultraviolet is the Earth and the atmosphere and the aurora glows just about as bright as the Earth, sometimes brighter, which is not the case in the visible. You can't see the aurora if you look up in the daytime if there's an aurora. It's just too bright. So FUV is a great emission to work at. This is a view looking out the side of the instrument, out the side of the spacecraft, north as we looked, and it looks like you're looking at the window of an airplane. A 787 window is almost exactly that shape, except your view is now from 600 kilometers altitude, and the window's open, and you have UV glasses on your eyes that one is doing one wavelength and one is the other. The left is a nitrogen emission, and the right is the oxygen emission. So you see some features, but you see the air glow layer. Richard, someone's excited. Excitement's building for our mission. So, and you see stars that are coming through our calibration. So these are our initial. In the end, we will slice and dice the data so we can bring it down faster. These engineering images took some time to bring down, but we're excited to show that. The last, I'll show you the MIGHTY image. Now, space station photography has provided us a lot of images of our science target for the MIGHTY instrument, which includes this yellow line, which we read off temperatures. That green line is at about 98 kilometers altitude, which is the green emission, the same you see in the aurora. It's just produced in a different way. And that red emission is the ionosphere. It's the bottom of the ionosphere as it's recombining. The MIGHTY imager, if I do this next, right, so the MIGHTY imager puts a little box, it has a little box 3 degrees by 5 degrees right off on the horizon, and it interferometrically introduces a fringe pattern on that scene, which is basically specifically the red or the green color is coded in that interferogram. And you can read off the change in that color by any motion of that interferogram. And it's a remarkable capability. We used to have to go to a lot of trouble. We went to a lot of trouble to make this work. It used to be even harder than this. But now we can separate those data into the red and green emissions. And if you look carefully, you can see the fringes in the green over here, and then, and the red. And you see the fringes a little finer in the red. It just is the way it is. It's baked into the instrument, and this is how it works. But any change in the color of that light, those fringes move slightly, and we can measure. Why would the color change? Well, it's Doppler shifting. We're reading off the motion of the atmosphere by watching those fringes move back and forth. One of the biggest inputs into moving those fringes is if the spacecraft's moving. Well, we know exactly our speed because we have a GPS unit. We know our speed to about 2 meters per second. So we can get the winds by looking at those fringes down to about 5 meters per second. That's our goal. What else is going on in this image? You're looking at succession of images from daytime to nighttime. And here we're going into nighttime. It's getting dark. We have shutters that we open them up at nighttime, and when it starts getting bright again, we drop them. So here we go into the daytime. Well, it's getting brighter, and then we drop the shutters so we can do our daytime science. There's a lot more green and red emissions in the daytime, but you can't see them from the space station. All of these movies, I'm just going to jump back because I love this movie, but is it going to play? Maybe. Well, if I do this, it's going to play. You never see that green emission in a daytime movie from the space station because they're not built to do that. There's a Nikon camera, and you go out and take a picture in the daytime. You don't see that. We have these really extensive, we've done a lot of work to make sure that we can do the same science in the daytime that we can in the nighttime to exclude all that extra light. So I think that's the end of my slideshow, and I think we'll all be happy to answer any questions you have.
Okay, so now we'll open it up to questions from reporters in the room. Do we have any questions? Anything? Do we have anything on the chat? No? Anyone? Going once, going twice? No? All right, well, if that's it, then we'll say thank you to our panel, and we'll resume again at 3:30. And I think they'll be around for a few more minutes for individual questions, right? Great, thank you guys so much. Wonderful.